Welcome to this video on the Boreal Zone, a critical component of the world's major biomes. In this presentation, we will delve into the unique ecosystems of the boreal forest and the tundra, exploring their defining characteristics, ecological importance, and the environmental processes that shape them. The boreal forest, also known as the taiga, is a vast expanse of needle-leaf forests stretching across the subarctic regions of the Northern Hemisphere. This biome plays a pivotal role in Earth's ecological balance, serving as a significant carbon sink and influencing global climate patterns. Situated just south of the Arctic Circle, the boreal forest experiences a continental subarctic climate characterized by long, harsh winters and short, cool summers. Mean annual temperatures in these regions range from -5 degrees Celsius to 5 degrees Celsius, with the warmest months averaging between 10 degrees Celsius and 15 degrees Celsius. Precipitation is relatively low, primarily falling as snow during winter months. The boreal forest stands as a testament to nature's resilience. Despite its harsh conditions, it supports a unique array of life and plays a crucial role in maintaining Earth's ecological equilibrium. Understanding and preserving this biome is essential for sustaining global biodiversity and combating climate change. Dominated by coniferous trees such as black spruce, jack pine, and larch, the boreal forest exhibits a simple yet resilient vegetative structure. These trees are adapted to the cold climate, with needle-like leaves that minimize water loss and withstand freezing temperatures. The soil, often underlain by permafrost, is acidic and nutrient-poor, limiting the diversity of plant life. The forest floor is typically carpeted with mosses and lichens, which thrive in the acidic and low-light conditions. The fauna of the boreal forest has evolved unique adaptations to survive the challenging environment. Species such as moose, wolves, and lynx have developed physiological and behavioral traits that enable them to endure the cold and scarce food resources. For instance, many mammals possess thick fur coats and fat layers for insulation. However, the limited food supply restricts species diversity, and only a fraction of migratory birds remain year-round. Beneath the vast expanses of the boreal forest lies a unique soil type known as podzol. These soils are the ecological foundation of needle-leaf forests, influencing plant growth, water movement, and nutrient cycling across subarctic regions. Podzols develop under coniferous forests in cold, moist climates. The thick layer of needle litter from spruce, pine, and larch trees slowly decomposes, releasing organic acids. These acids drive intense leaching, washing soluble minerals and nutrients down through the soil profile. This process shapes the soil's distinctive layers and contributes to its nutrient-poor nature. Podzols are easily recognizable by their layered structure. At the surface, a thin organic layer is followed by the E-horizon, an ashy gray zone where intense leaching has removed most minerals. Beneath this lies the B-horizon, rich in iron, aluminum, and organic compounds, giving it a darker, more compact appearance. This contrast highlights the movement of materials within the soil and the long-term impact of acidic forest litter. Podzols are generally acidic and low in nutrients, which limits the diversity of plants that can thrive. Yet many boreal species, such as mosses, lichens, and hardy conifers, are specially adapted to survive in these conditions. At the northern edges of the boreal forest, where temperatures plunge and permafrost dominates, a different type of soil takes over: gelisols. These soils reveal the profound influence of cold on soil formation and ecosystem dynamics. Gelisols are young soils with minimal profile development, a direct consequence of the frigid climate. The persistently low temperatures slow down organic matter decomposition and limit chemical weathering, leaving the soil poorly developed compared to warmer regions. A defining feature of gelisols is the presence of permafrost, with frozen layers typically found within 2 meters of the surface. This frozen substrate profoundly affects water drainage, root penetration, and nutrient availability, making gelisols some of the most challenging soils for plant growth. Because of the permafrost layer, gelisols are very poorly drained. Water tends to accumulate on the surface during the brief summer thaw, creating soggy conditions and sometimes forming bogs or peatlands. Soil development remains slow, and the thin active layer that thaws each summer supports only specialized tundra vegetation, or the hardiest boreal species. Gelisols are common in the northernmost parts of the boreal zone, including Alaska, northern Canada, and Siberia. Wherever the climate imposes near-permanent frost, gelisols dominate the landscape, marking the transition from boreal forest to Arctic tundra. Beyond the boreal forests and frozen soils lie the tundra ecosystems, where life endures in some of the harshest environments on Earth. These regions are defined not just by cold, but by extreme seasonal variations and unique adaptations of flora and fauna. The Arctic tundra occupies the extreme northern regions of Russia, Canada, and Alaska. Here, the length of daylight varies dramatically across the year, from continuous sunlight in summer to complete darkness in winter. Winters are long, dark, and bitterly cold, often lasting 6 months or more. The alpine tundra, in contrast, occurs at high elevations across all latitudes, from tropical mountains to temperate ranges. Despite being at lower latitudes than the Arctic, the harsh conditions of altitude, cold temperatures, strong winds, and thin soils make alpine tundra remarkably similar to its Arctic counterpart. Plants are small and compact, often growing in mats to resist the cold and conserve moisture. Vegetation is sparse and low-growing, including mosses, lichens, and small shrubs. The short growing season and permafrost limit plant diversity and productivity, creating a fragile ecosystem finely tuned to its environment. Both Arctic and alpine tundra ecosystems play a crucial role in carbon storage, climate regulation, and biodiversity at extreme conditions. Their fragile soils and vegetation are highly sensitive to climate change, making them important indicators of global environmental shifts. Whether at the poles or atop towering mountains, tundra ecosystems demonstrate nature's resilience. Life persists where conditions are harshest, offering a window into the limits of adaptation and survival on Earth. Tundra soils are a reflection of the extreme environment in which they form. Due to slow biological activity in the cold, these soils often exhibit poorly developed horizons, with minimal layering compared to more temperate regions. Nutrient availability is limited, resulting in low fertility and low organic matter in mineral soils, though localized peatlands can accumulate significant organic deposits over time. Seasonal thawing creates an active layer that melts during summer, often leaving soils waterlogged. This saturation further restricts plant growth and affects soil processes, shaping the delicate tundra ecosystem. In the cold, dynamic landscapes of the Arctic and subarctic, some soils remain almost entirely undeveloped, reflecting the youth of the terrain or the harshness of the climate. These are known as entasols, and they tell a story of slow soil formation under extreme conditions. Entasols are commonly found in areas with recently exposed surfaces, such as glacial outwash plains, river terraces, or other young landscapes. They are the least developed soils, often lacking distinct pedogenic horizons and showing minimal mineral alteration. The slow pace of weathering and limited vegetation growth, common in cold environments, means that entasols rarely develop the layered structure seen in older soils. As a result, horizon development is minimal and nutrient availability tends to be low. Despite their simplicity, entasols are widespread in high latitude and recently glaciated regions, forming the substrate for pioneer vegetation and influencing drainage and water retention. They represent the starting point of soil development, providing insight into the early stages of ecosystem establishment in cold regions. In the cold and waterlogged landscapes of the tundra, some soils are composed almost entirely of organic matter. These soils, known as histosols, are a direct result of the slow decomposition of plant material under saturated and frigid conditions. Histosols form where waterlogging prevents complete decomposition, allowing organic material, primarily mosses and sedges, to accumulate over time. Instead of mineral soils, these deposits create thick layers of peat, which grow upward as new organic material accumulates. These soils are saturated with water, highly acidic, and nutrient-poor, yet they play a critical role in carbon storage and ecosystem function. Despite their apparent barrenness, histosols support specialized tundra vegetation adapted to wet, cold environments. Histosols are common in wet tundra areas, including bogs, marshes, and poorly drained lowlands throughout Alaska, northern Canada, and Siberia. They mark regions where water and cold dominate soil processes more than mineral weathering. Among the soils of boreal and tundra landscapes, some occupy a transitional space between young, undeveloped soils and fully mature profiles. These are known as inceptisols, and they reveal the gradual progression of soil development under cold conditions. Inceptisols are weakly developed soils, lacking diagnostic horizons that define more mature soils like podsols or histosols. They form in areas where climate, vegetation, or topography limits soil development, such as sloping terrains, floodplains, or recently glaciated regions. While more fertile than podzols, inceptisols are still nutritionally limited by cold temperatures. Organic matter accumulates more slowly than in temperate zones, and chemical weathering remains minimal, resulting in soils that are intermediate in maturity. These soils are common in transitional zones, including mixed forests and the edges of tundra regions, bridging boreal ecosystems with temperate ones. Their widespread presence in high-latitude floodplains and glacial landscapes reflects the ongoing processes of soil formation in challenging environments. Inceptisols illustrate the slow, ongoing process of soil formation in northern landscapes. They are a key link between young, undeveloped soils and fully mature profiles, providing insight into the dynamics of ecosystems at the edge of the boreal and tundra regions. The tundra is home to a variety of soils, each shaped by extreme cold, short growing seasons, and waterlogged conditions. Understanding these soils is essential for appreciating how tundra ecosystems function and persist under harsh environmental constraints. Each tundra soil type reflects the unique combination of cold climate, water saturation, and limited biological activity. From frozen gelisols to organic rich histosols, these soils shape vegetation patterns, influence hydrology, and store carbon, forming the backbone of one of the planet's most extreme ecosystems.